Hello all, we are going through chapter 7 now, so quantum theory and the electronic structure of the atom. So in chapter 7a, the first topic here, understanding the organization of the electromagnetic spectrum. So for some properties of waves, and we denote the electromagnetic spectrum as being made up of different wavelengths. We'll look at that in a little bit. So the wavelength is the distance between identical points on successive waves. So let's say we pick this top portion and then this top portion, so it needs to be on identical points. That distance is our wavelength, denoted as lambda. So this Greek symbol lambda, so that is how we denote wavelength. The amplitude of a wave is the vertical distance from the midline, so here, of a wave to the peak or the trough. So the peak is the higher end, the trough is the lower end. So peak and trough. Amplitude then is a vertical distance from this midline either to the peak point or also from the midline to the trough point. That's going to be the same distance because this line here is the midline. So that is amplitude. Next, a really important definition here is frequency. This is actually another Greek symbol that you might hear as nu. So frequency, or nu, is the number of waves that pass through a particular point in 1 second. So frequency is really just how many times does that wave pass through per second. So how does that work? Well, this wave is propagating and it's heading in some direction. So this wave is kind of moving like this and it's moving forward. So if we watch this wave pass through some specific point, so that's our eye looking at this. If we were to stand right here, we would see the wave pass through. So we'd see the peak, then we'd see a trough, then we'd see another peak, etc., because it has direction, it's moving. So if we were to stand right here or look right here, the frequency is the number of waves that pass through a particular point within 1 second. So how many times does it happen per second? What is the frequency? Let's say we were standing here and this wave passed through 5 times. We saw a peak pass through 5 times. That would be a frequency of 5. So for example, 5 cycles per second. The units you're going to see with frequency is a hertz. So 1 hertz is the same as 1 over a second. And then from negative exponents, we could also denote this as seconds to the -1. Wavelength is going to be a distance, same as amplitude. The classic distance we use, or distance unit, generally in nanometers, at least for the visible wavelengths. But when we come to this slide, we'll also see we can have micrometers, millimeters, just plain meters, and even as long as kilometers. So for wavelength, nanometers for the visible wavelengths, you'll also see meters, millimeters, even kilometers, even as small as picometers. Then amplitude will be a distance unit as well, so it could be nanometers, meters, etc. And one equation here, the speed of the wave is lambda times the frequency. Let's see how those units work out. So speed of wave is lambda. Lambda is our wavelength. Let's say we're working in units of nanometers. Then this frequency term here, we could say as a hertz, that's the same thing as how many times in 1 second, so 1 over seconds. So we're taking a unit of distance times a frequency, so 1 over seconds. That means the speed of the wave here would be reported in nanometers per second. We could also have meters per second, just depends on what unit of distance you put in here for the wavelength. Could be nanometers, meters, millimeters, etc. So here is the first equation of a few we'll go through in chapter 7 related to waves. So light acts as a wave. It has motion, it has a wavelength associated with it. It has amplitude associated with it, it has a frequency, how many times does it pass through a certain point per second. So Maxwell was a scientist that proposed that visible light consists of electromagnetic waves. So not only do we have an electro component, we have a magnetic component to visible light. What does that mean exactly? Well, it means these are going to be perpendicular to one another, and essentially all waves are made up of this one direction or one component, that's the electric field component. Then at a 90-degree angle to that, we have a simultaneously magnetic field component of that wave. What does this 90-degree component look like? Well, we could have something happening in this plane, which is our XY plane. Then 90 degrees to that, we can have something happening in the Z and the X plane. So the ZX plane for one component, and then the XY plane for another component. So we think of the wavelength of light propagating this direction, and also another simultaneous wave happening 90 degrees to that. So when you hear electromagnetic spectrum or the electromagnetic radiation, this is the emission and transmission of energy in the form of electromagnetic waves. So this happens to be true for visible light and other areas of our electromagnetic spectrum. And we'll look at the spectrum here in just a few slides again. So these wavelengths of light have both electric and magnetic field components. This is why you may have heard this called electromagnetic spectrum, or it's an electromagnetic wave. So there's the electric component and the magnetic component to these different wavelengths. Here's the next equation we'll see in chapter 7a. So all electromagnetic radiation follows this equation. So lambda we know is wavelength, nu or frequency, then c here is the speed of light in a vacuum. This is a standard constant value. This is 3.00 times 10 to the 8th meters per second, the speed of all light in a vacuum. Let's check out how these units work out here. So c is in units of meters per second. Then lambda, let's say we selected one as a wavelength of meters, let's say. Then nu or frequency, again, is 1/seconds. So wavelength times frequency is going to equal a meters per second, like we saw with the last equation. So this is the speed of some general wave, but generally we're going to work with this equation, assuming the speed is the speed of light in a vacuum, or the standard constant value we'll plug in here. So c, the speed of light constant in a vacuum, 3.00 times 10 to the 8th meters per second. So let's see how we're going to use this equation throughout chapter 7. Before practicing using that equation, let's go ahead and stop and look at this practice problem. So we have a few different types of electromagnetic radiation. So an electric component and a magnetic component, different types of radiation are listed in the table below. These are all technically types of radiation. That's just something that has a wavelength associated with it. You might hear, oh, you're being exposed to radiation. It depends on what kind of radiation it is, if it's going to actually be potentially dangerous to the cells and even the DNA in your body. Gamma rays are dangerous radiation. X-rays can be dangerous radiation. Radio waves are found all around us, and they're typically found to be not dangerous. So we're going to complete the table by ordering these types of radiation by increasing frequency. So frequency again, think nu, think this is in units of hertz. What is a hertz again? It's 1/second, or 1/seconds. So we're going to rank these by increasing frequency, wavelength, which we'll denote as lambda, typically meters or nanometers or millimeters, etc., and by the energy per photon. What are the units of energy typically? Well, we saw in chapter 6, we used joules to describe energy, joules or kilojoules. So we're going to select 1 in the second column for the type of radiation with the lowest. So 1 for the lowest, 2 for next, and etc. We need to do this for radio waves, microwaves, ultraviolet radiation like we get from the sun, and green, which is visible light. So we can see the color green based on the wavelength that green light propagates at. So we can see that wavelength. That's why we can see green. We can't see radio waves because of their certain frequency and wavelength. We also can't see microwaves with our naked eye. Same with UV radiation. We can't see those with our naked eye because of the frequency and the wavelength of those types of radiation. So we looked at this a moment ago. Let's talk more about this. So different facts about electromagnetic radiation. So electromagnetic radiation is divided into different types or can be thought of as bands of radiation. Each band includes all radiation with a particular range or frequency of wavelength. So a certain band that's gamma rays, that would be in the range of 1 picometer of wavelength. And then 1 zeptohertz is technically that Z out front. We did not look at this prefix, so don't worry about this one. This is just to give you an example. So from this diagram, we can see that the electromagnetic radiation with a wavelength between this range of 1 millimeter to 1 meter, which then corresponds to a frequency of about 1 gigahertz to 1 terahertz. This is in the range or the band of microwave radiation. So we're focused on this band or range here. Notice that in the microwave range, again, we're going from 1 millimeter to about 1 meter for the wavelength. This corresponds to this range of frequencies from about 1 gigahertz to 1 terahertz. This is helping us show that wavelength and the frequency are extremely interconnected. If we know the wavelength, we can get the frequency. If we know the frequency, we can get the wavelength. We just saw that equation here, right? So wavelength and frequency are connected through this constant standard value of the speed of light. If this value doesn't change, then we can know the frequency and calculate the wavelength. Again, if this value doesn't change and we know the wavelength, we can calculate the frequency. So that electromagnetic spectrum is based on this equation that connects lambda to frequency through the speed of light. And again, what are our units here? Well, this is going to be meters per second. This is 1 over seconds, and this is going to be meters. So these units work out. We can connect any frequency value to any lambda. We can connect any lambda to any frequency value. And then based on the lambda or the frequency, we say those are microwaves, infrared radiation, UV radiation, X-rays, gamma rays, radio waves, or even this range of visible light. So this is the only range out of all of this range of radiation that we can actually see with the naked eye. So from a human's eye, we can't see anything beyond here. We can't see anything beyond here. We can only see this small range of radiation. So let's focus in on the visible wavelengths for a second. So visible light, it's unique because we can actually see it with the naked eye. So visible light is electromagnetic radiation with a wavelength between 400 nanometers and 700 nanometers. 400 nanometers is our violet color. A longer wavelength of 700 nanometers, that is our red color. So the exact color that we see depends on the exact wavelength, where light with the longest wavelength, so right, this is the longest, 700 is longer than 400. So light with the longest wavelength appears red, while light with the shortest wavelength appears a deep blue or violet color. So let me specify longest wavelength, and then here is our shortest wavelength. These are indeed the same colors we see in a rainbow. So sometimes people say Roy G. Biv to remember that indigo is in there as well. It's not just red, orange, yellow, green, blue, purple. It's blue, indigo, violet. So blue, sort of an indigo is like a deep blue, purple, and then violet. So Roy G. Biv is one way to remember the order of visible wavelength. So longest to shortest wavelength. So you should be familiar with the fact that red light has the longest wavelength, blue or indigo or violet, a deep blue, mostly we think about violet having the shortest wavelength over here, then green falls about right in the middle. So 400 and 700 right in the middle would be about 550 nanometers. So again, this is just zoomed in very specifically from this whole range of electromagnetic radiation. We can only see this small range of wavelengths between 400 and 700. There are things like UV goggles you can put on to see other types of radiation. So this is all we can see with the naked eye. But from this slide, it's clear there's a lot else happening other than just the visible range of wavelengths. Here now is another important equation connecting energy, this is Planck's constant, and then frequency. So somewhat confusingly, this can be denoted still as nu, like we saw on the last slides. So normally I'll write out energy is equal to Planck's constant times nu or frequency. Just like we had a constant for speed of light, we have another really crucial constant to keep in mind. So from the scientist Planck, this symbol H denotes Planck's constant. Very importantly, this value of 6.62607 times 10 to the negative 34. Now take a look at the units of joules per hertz. So let's break down these units. We know joule is for energy, hertz is for frequency. Let's see how this works out in this equation. So energy, we're going to see that in joules. Planck's constant is a joule per hertz. Then frequency or nu is hertz. So be careful with frequency because this is hertz in the numerator, but that's equal to 1/second, where second would be in the denominator. So let's take a look at that. If we know it's joule over hertz or a joule per hertz, that's really equal to a joule over 1/2. Then we can multiply by the reciprocal. That means Planck's constant can also be thought of as units of joule seconds. Joule second is the same thing as a joule over a hertz. So the 6.626 joule seconds or joule over hertz. And frequency typically denoted as nu and not generally as lowercase f. Based on this relationship, we need to make some important connections between the frequency and the energy of some wave. When some wave has a higher frequency, a greater frequency, that's going to have a higher energy, or specifically called a higher photon energy. Generally, we can just think that it has a higher energy. If something has a lower frequency, if the wave has a lower frequency, that's going to have a lower energy. Let's compare X-rays to visible light. Which one has a higher frequency? So here we have X-rays, here we have visible light. Frequency is increasing this direction, so X-rays have a higher frequency compared to visible light. So this is just talking about the frequency. One connection I want to make here before we talk about energy and frequency is notice that as frequency increases this direction, wavelength actually increases the opposite direction. We'll practice doing some calculations here, but you should notice now as wavelength increases, the frequency decreases. As wavelength decreases, then it'd be in this direction, frequency increases. The way I like to visualize this is, let's say we have a really long wavelength, it's going to have a low frequency. How can we visualize that? So if this is a really long wavelength, it's going to pass through some certain point. And let me draw on the midline here as well. So it's going to pass through some certain point, less times per second with a longer wavelength. Longer wavelength, a smaller frequency. It passes through some point, less times per second, because the wavelength is longer. Now for a shorter wavelength, we're going to picture something like this. So as I drew this wave in blue is going to pass through a certain point way more times per second than the one with a longer wavelength. So a smaller wavelength, a higher frequency, again, a longer wavelength, a shorter frequency, a shorter number of times it passes through a point per second. Now we can connect frequency to energy, right? So we just saw that as the frequency decreases, energy also decreases. As the frequency is higher, that means energy is higher. So longer wavelength, shorter frequency, less energy. Red light has less energy than violet light. Shorter wavelength, higher frequency, higher energy. This blue one with a shorter wavelength but a higher frequency, that has a lot more energy associated to it compared to the green, smaller or shorter wavelength. So we should feel comfortable connecting wavelength, frequency, and energy for all different points on the electromagnetic spectrum. Let's practice here. Let's say that red has the longest wavelength. From what we just learned, that's going to have a shorter frequency or a smaller frequency. So longest wavelength, shortest frequency, and smallest amount of energy. Violet light has the shortest wavelength. That means the higher of the frequencies and the higher of the energies. So X-rays have much higher energy than visible light because they have a higher frequency. Frequency of X-rays greater than that for visible light, so X-rays have a higher energy. Okay, so added that notation in here. And we could even say that energy is the highest at this point, energy is the lowest at this point. Higher frequency, higher energy, lower frequency, lower energy. Radio waves have the lowest energy. That's why they're fairly safe compared to gamma rays that have a really small wavelength, really high frequency, and a lot of energy associated with gamma rays. Then the energy of visible light is much higher than that of radio waves, again for the reasons I just mentioned. So in solving our problem, I'd probably lay out something like this, where I'm showing the longer wavelength, the smaller frequency, the smaller energy. Over here, a smaller wavelength, a greater frequency, and a greater energy. Let's place each one of these on this range. So we have radio, micro, green light, then UV radiation is here. So radio, micro, green light, UV radiation, now we can more easily rank all of these. So we're putting 1 as the lowest, 2 for the next highest, etc. Let's do frequency and energy. Let's rank those. Radio has the lowest frequency, the lowest energy, then we go up to UV having the highest frequency, the highest energy. Let's do wavelength now. So the smallest wavelength is for UV, then next for green, then for micro, then for radio. This has the longest wavelength over here. So this column is going to be the same ranking as this column. Frequency and energy are directly connected, directly proportional. So radio waves have the smallest energy and the smallest frequency, but the highest wavelength or the greatest wavelength. Microwaves then, they're ranked second for the frequency and for the energy, third for the wavelength. UV then, for the frequency and energy, they are the highest. Then UV radiation has the smallest wavelength. For the green light now, frequency and energy both ranked third. Then for the wavelength, it's ranked second. So this is one way to solve it. I like to denote it like this so I don't get confused, especially when we're saying 1 is the lowest and 4 is the highest. So 1 lowest, 4 is highest. Let's check our final answers here. So this is our final answer for this set of radiation, ranking in order for frequency, wavelength, and energy. Now in this next topic, we're going to go through interconverting wavelength and frequency of the electromagnetic spectrum. So we're going to use those different equations and actually apply them to some practice problems. This is another nice depiction of the electromagnetic spectrum. We can see X-rays, UV, visible wavelength, heat lamps, which is from infrared radiation, microwaves, radio waves, and different types of radio waves here. So FM versus AM, those have different wavelengths and different frequencies. Then again, violet is 400 nanometers, so the smaller wavelength. 700 nanometers for visible light is red. That is the largest wavelength. Largest and smallest within the range of visible light. It's really important to connect wavelength to frequency to even energy. 10 to the negative third, that's a very small wavelength. Frequency here, 10 to the 20th, that's a very high or a very large frequency. That also means we have a large amount of energy. On this side, 10 to the 13th, that's a very long or large wavelength. Then that corresponds to a smaller frequency and therefore a smaller amount of energy. Again, radio waves, less dangerous, a less amount of energy, especially compared to X-rays and gamma rays. So gamma rays, the most energetic with very short wavelengths. X-rays are less energetic than gamma rays, followed by UV light, which is still used in tanning beds. So of course, not super safe to be in a tanning bed because there's direct UV radiation on your skin. Then on this side of the visible spectrum, so sometimes you'll see it split up as this side of the visible spectrum, so the smaller wavelengths, the larger frequencies, then this side of the visible spectrum with larger wavelengths and smaller frequencies. So infrared light, also denoted as IR, used in heat lamps, is less energetic than visible light. Right, we're getting smaller frequencies, smaller energy. Microwaves then are less energetic than infrared light, and radio waves are the lowest energy waves of the electromagnetic spectrum. That means also they have the highest wavelength then, right? So be really comfortable connecting wavelength, frequency, and energy. Then focusing on visible light again, this is less energetic than UV light. And we know visible light ranges from 400 nanometers to 700 nanometers. Let's say now we have a frequency of 105. What is that capital M again? Capital M is for mega. So we have a frequency, we want to calculate a wavelength. We're going to use those different equations we've seen so far and include a unit conversion. So the really important equation we've seen at this point is the speed of light is equal to the frequency times the wavelength. The speed of light is always known. It's that 3.00 times 10 to the 8th meters per second. I'll also show you a more specific number to use for the speed of light. So about 2.997 or 2.998 times 10 to the 8th meters per second. So this number is slightly unrounded. You'll get a slightly more accurate answer using this value for C, the speed of light, rather than this value. And to be clear, this is raised to the power of 8 and raised to the power of 8. So we know C, we're also given the frequency in megahertz. So we were given the frequency, we're going to calculate the wavelength. At least at this point, we can rearrange this equation. We know we're going to solve for wavelength is the speed of light over the frequency, has to be in the correct units. So units, definitely we will check those. C we know is meters per second. Our frequency right now is in units of megahertz. We know a hertz is 1 over a second. So we'll need to deal with this mega here out front. So for that mega conversion, 1 megahertz is equal to 1 times 10 to the 6th, just hertz. So let's do this conversion. We have 105 megahertz. We just want this in units of hertz, so we can have it in a 1 over second. Then the units will work out for the speed of light that is in meters per second. not meters per megasecond. So we need to get rid of that mega here. So to set up this conversion factor in the correct orientation, we'll say that 1 megahertz is equal to 1 times 10 to the 6 just hertz. So here I got 1.05 times 10 to the negative 4th hertz. That's the same thing now as units of 1/second. So we want to find wavelength. We know the speed of light. Let's go ahead and put in the slightly more accurate version of the speed of light constant. So meters per second. So meters per second, we're dividing by the frequency. That's really like multiplying by the reciprocal. So let's go ahead and put in 1.05 times 10 to the negative 4th. Instead of writing out hertz, I like to write this out as 1/seconds. Then I can see if my units cancel out slightly more easily. So this is in units of 1/second. I don't really need that 1 in here. It's just this number over a second. For the units here, let's see. We have meters per second over 1/second. That's really like multiplying by the reciprocal, so seconds over 1. That means seconds and seconds cancels out both in the denominator and the numerator. So we get meters as our unit in the end, and that is the unit we want for a distance like wavelength. We could be asked to further convert this into nanometers, for example, but definitely wavelength, we want to be a distance unit like meters. So this number divided by this number, oops, this is not correct. I made an error here by not putting parentheses around 10 to the 6th. So I must have made some calculator error here. Really what we got for this, 105 times 10 to the 6 should be a really large number. So here I'm getting 1.05 times 10 to the 8th units of hertz. That still is the same thing as 1/second. Now I need to plug this in here. So this is really 1.05 times 10 to the 8th. So a really large number, still 1/seconds. Doing this division, I get 2.8476. No exponents here, just in units of meters. We only want 3 sig figs in the end, so this is just 2.85 meters. Again, you might be asked to eventually convert this into nanometers, millimeters, etc. So we would do this first, then do the next unit conversion if we needed to. Then from the calculator error I must have made, it is important to put 1 times 10 to the 6 in parentheses. And just a general reminder to be really careful about putting in the correct numbers into your calculator and checking, did my answer make sense from that calculation? So this number is correct. I put that in here. Then I solve for my wavelength just in units of meters and with 3 sig figs. So we decided on 3 sig figs to get this final answer. The reason we don't care about the speed of light in terms of the number of sig figs, so this 2.998 goes on indefinitely. And even if we use 3.00 times 10 to the 8th, these two numbers, both versions for the speed of light constant, those are exact numbers. So for the speed of light itself, don't worry about the number of sig figs in the speed of light. Just look at the other numbers you're provided with in the problem. So the sig figs in the speed of light do not impact the sig figs in your final answer. So this is our final answer. I do want to point out example 7.1 is another good one to check out. There you're going from wavelength to frequency. So still using the same equation, but going from wavelength into a frequency value this time. As always, let me know if you have questions about these examples or anything else we're going over. Let's do something similar. Now we're going to interconvert wavelength, frequency, and energy. And so next time someone asks you your favorite color, I challenge you to tell them a wavelength in nanometers. Oh, maybe 700 nanometers because you really like the color red. So we've seen this equation before. We're going to use it now. So energy is equal to Planck's constant times the frequency. Notice now that frequency is again denoted as nu, or sort of a italicized V. So this symbol, nu, this is for the frequency. Then again, we're going to be using Planck's constant here. Notice the difference in units. It's no longer a joule over a hertz, because as we saw, as we practiced, that's the same thing as a joule second. The hertz is the same thing as a 1 over second, then this joule here is our energy unit. Both Planck's constant and the speed of light are both considered exact values, so they don't play a role in determining the number of sig figs in your final answer. So this is another exact number like the speed of light. Another sort of interesting tidbit here, so when solids are heated, they emit electromagnetic radiation. The wavelength of radiation that a hot object emits depends on the temperature that it was heated to. So we call this radiant energy when a hot object actually emits energy. This is sort of heat energy, or also called radiant energy. So a heated object actually emits light that looks like a wave, a classic wave. That radiant energy wavelength, though, is not visible. We can't see the actual radiation coming off of a hot object. If there is some water around that hot object, we could see steam coming off of the hot object, but we're not going to see the actual wavelengths of that radiant energy. And so we saw that it was called photon energy earlier, and I told you not to worry too much about that wording, just to think about a higher frequency having higher energy in general. Well, what a photon is, to specify here why it was called photon energy, I still want you to think about it essentially in terms of energy, but a photon is a particle of light. So there's this concept that light has duality to it. So light has duality. It has both wave nature, so like what we looked at, and particle nature, or sort of photon nature, where particle nature thinks of light as these pockets of energy, or photons. The way we're going to treat light in this class, we're going to think of it mostly as waves. There are some additional equations we'll practice with here. So Planck's constant times the frequency is equal to kinetic energy plus work. This work variable relates to this image here. So here we have some incident light at some wavelength. It's hitting some piece of metal. When this incident light hits a piece of metal, let's say for example we were dealing with copper metal or even gold metal. So we know copper metal, gold metal, all of the metals on the periodic table, these all are composed of atoms. We know our atoms contain protons, neutrons, and electrons. It turns out when incident light hits a sheet of metal, then electrons are released from that metal. Then these electrons can be detected based on a changing voltage within the apparatus. Why would the voltage be impacted by electrons being released? Well, we can see a change in the voltage because electrons are negatively charged. Electrons are negatively charged, and so the voltage is detecting the change in negative and positive charges. And so because light caused an emission of an electron from a piece of metal, and we could see that by a change in the voltage because electrons are negatively charged, so the voltage will be more negative as we're emitting more electrons, as the metal is emitting more electrons. And so along with a series of experiments, Einstein, along with some other scientists, concluded that light behaves as both a wave and a particle. So it has this wave-particle nature duality. The key points I want you to take away is that remembering that metals are composed of atoms, all elements are composed of atoms, where atoms contain protons, neutrons, and electrons. And importantly, electrons can be emitted from atoms. So some electrons are not incredibly bound to their nucleus. Some electrons can be emitted from the outer shells of the atom. So if an electron is way out here, it can actually be plucked away from the atom. And we'll talk a lot more about how these electrons surround the nucleus. Then also keeping in mind that electrons are negatively charged, that's another big takeaway, and the fact that light has both wave and particle nature. So coming back here, this W term is the work function and depends on how strongly the electrons were held on that metal. So we're going to practice with this equation as well. Rearranging this, we can solve for kinetic energy is equal to Planck's constant times the frequency, then minus the work term. And again, the work depends on how tightly or how strongly those electrons were held to the metal before being emitted. Then another cool application in this chapter is thinking about lasers. So if you have a laser pointer or you've ever played with lasers, doing so safely, because this radiation here can be really dangerous to the human eye. Okay, so of course we don't want lasers to be in direct contact with the human eye or a cat's eye. If you ever play with a cat with a laser pointer, you don't want the laser to come into direct contact with any sensitive parts of the body like an eye. When we zoom in though on what the laser actually looks like, this laser is emitting a certain wavelength, so a wavelength of about 694.3 nanometers. In the visible spectrum, what color would that look like? Well, we know that's approximately close to 700 nanometers, which we know appears red visually. So if you have a laser, it depends on what is inside the laser, but it's going to emit the same wavelength, and depending on the color of the laser, now you know approximately what wavelength it's emitting. For example, chromium ions, when they're excited in the laser pointer or the laser rod, depending on what kind of laser you're using, they emit a photon of light at 694 nanometers. If we know this wavelength of 694 nanometers, we could certainly calculate a frequency, right? And from the 694 nanometers, we are expecting that to appear red, and so it does for this laser. Let's try this practice problem. So we have 163 kilojoules per mole to break a nitrogen-nitrogen single bond. We're going to get a lot more into bonding and drawing out structures. If we're told there's a single bond between two nitrogen atoms, that's going to look like this. Other kinds of bonds we've seen are the quote kinds of bonds, so a quote ionic bond. The reason it's in quotes is because that's more of an electrostatic interaction. It's not a physical bond. But they are held together tightly, the two atoms, because of their opposite charges. Here we're going to calculate the maximum wavelength of light for which a nitrogen-nitrogen single bond could be broken by absorbing a single photon. So just as metal could emit electrons if it interacts with some wavelength of light, we can actually use radiation as well to break bonds. In dealing with UV radiation especially, we're going to break certain bonds, or we could manipulate our DNA in a really bad way, right? So certain radiation can actually break bonds, and that's really bad if it's bonds within some important component of the human body. That's why we need to avoid different dangerous types of radiation, because it can actually break bonds in our body. Radio waves and other safer ways have not been shown to do that. But of course, there are certain precautions to take, especially with X-rays. And if you're pregnant, for example, then you don't expose a new fetus, a growing fetus, to strong radiation like this or to high energy radiation. So we're going to figure out the wavelength from this information here. This important equation that we've seen, so energy is equal to Planck's constant times the frequency. So the frequency and the photon energy are connected through this important equation, where E stands for the energy of each photon of the radiation, or just energy. Nu here is for frequency, then H is Planck's constant. Planck's constant we know, that's a constant, it doesn't change. We were given energy. We were given energy in kilojoules per mole. So energy in kilojoules per mole, ideally we would just have this in kilojoules, so we'll see how we can deal with this mole term in the denominator. Then we don't know frequency. In the problem, we're not asked to solve for frequency though, we're asked to solve for the wavelength. So once we calculate frequency, we can then solve for the wavelength from this equation that we also saw previously. So once we solve for frequency, then we do know the speed of light. We can solve for wavelength. It'll just take a few steps. When just solving for frequency, we can rearrange this equation so it's energy over Planck's constant. Once we know frequency, again, we can plug that in here, or plug it in here to get our wavelength. So as mentioned, that E value needs to be energy. Here, though, we weren't given just energy in joules or kilojoules. Here we're given energy as 163 kilojoules per mole. We need to deal with this per mole. We need to get rid of it, so we just have units of kilojoules or joules. So from chapter 3, we know we can connect 6.022 times 10 to the 23 of anything per mole. This is Avogadro's number. So to get rid of this per mole basis, we need to take 6.022 times 10 to the 23rd per 1 mole. So this 163.3 kilojoules per mole, that is the energy required to break 1 mole of nitrogen-nitrogen bonds. We don't want a whole mole of nitrogen-nitrogen bonds. We just want it on a per 1 bond basis. So here for us, this is really N bonds, right? So this is 6.022 times 10 to the 23rd, anything per 1 mole. Even nitrogen-nitrogen bonds per 1 mole. This many, Avogadro's number, nitrogen-nitrogen bonds per 1 mole. It's sort of like thinking about how much nitrogen we have in 1 mole. Here we're getting really specific though. It's the number of nitrogen-nitrogen bonds in 1 mole. And more specifically, nitrogen-nitrogen single bonds. When we draw structures, we're going to look at single, double, and triple bonds. So here moles and moles would cancel out. It's this number of kilojoules divided by Avogadro's number. Then because we want this in terms of joules, because Planck's constant is in terms of joules, let's go ahead and convert this into joules. So there are 1,000 joules in 1 kilojoule. So we're going to take all this, then multiply it by 1,000. This equates to 2.7067 times 10 to the 19th joules. That is the term we can use to plug in for E. So E has to be in joules, not joules per mole, not kilojoules technically because Planck's constant is in joule seconds. So you want this E term to be in joules. Planck's constant is joule per hertz, or same thing as a joule second. So joule second or a joule per hertz. We'll practice using Planck's constant here in just a second. So let's plug in what we know for E, plug in Planck's constant, get a frequency value, then plug in that frequency to get a wavelength. So this is our E term. For Planck's constant, let's use the joule second unit. So 6.626, I usually just use 6.626 rather than this 07. So 6.626 times 10 to the negative 34 joule seconds. Do our units work out for what we expect for frequency or nu? For frequency or nu, we expect a hertz or a 1 over seconds. So here joules and joules cancel out, so then we are indeed left with the correct units of 1 over a second. So here indeed we are left with the correct units of 1 over seconds. This number comes out to 4.0849 times 10 to the 14th, same thing as a hertz, same thing as a 1 over second. Now we know the frequency. Let's plug that into the speed of light is equal to frequency times lambda. So let's solve for lambda now. Rearranging this, we're going to have lambda is equal to the speed of light over the frequency. So here, let's use the slightly more accurate speed of light, or 2.998 times 10 to the 8th meters per second. The frequency term we just calculated on the last slide was at 4.0849 times 10 to the 14th per second. Here's our values. Let's see how just the units do work out. So C, speed of light, is meters per second. Frequency is 1/second. We can multiply by the reciprocal here. Seconds and seconds cancel out. Seconds and seconds cancel out. This leaves us just units of meters, which is what we expect for lambda. So maybe not as clear to see when written like this, but here we're showing that seconds and seconds cancel out. That leaves lambda, or wavelength, to equal 7.3390 times 10 to the negative 7th meters. This is unrounded at this point. Because Planck's constant doesn't matter and the speed of light doesn't matter in determining the final number of sig figs in our final answer, we should just go back up to the main problem, and we have this value here that has 3 sig figs in it. So our final answer should have 3 sig figs in it. So 7.34, it'll be times 10 to the negative 7th meters. So 7.34 times 10 to the negative 7th meters. Because we're going to need the meter to nanometer conversion, we're going to need this a decent amount in Chapter 7. Let's review this unit conversion. So a nanometer is really, really tiny. So 1 meter is equal to 10 to the negative 9th nanometers. So because a nanometer is really, really tiny, we're going to have a whole lot of nanometers in 1 meter. That means for every 1 meter, we're going to have 10 to the 9th nanometers. For example, if we have 1 meter stick, we're going to have a whole lot of millimeters in 1 meter. We can't measure nanometers with a meter stick, but you get the idea that within 1 meter, we're going to have a whole lot, a large number of nanometers. So times 10 to the 9th rather than 10 to the negative 9th. Using this unit conversion, we would need to say that 1 meter in the denominator is 10 to the 9th, or 1 times 10 to the 9th, same thing, because we're just multiplying this by 1 nanometers. So this value times 10 to the 9th does get us 734. Now our units are no longer meters, but in units of nanometers. In doing this multiplication as well, be really careful about your parentheses. For example, 7.34 times 10 to the negative 7th, it's 10 to the negative 7th in parentheses. That needs to happen first. If you didn't put the parentheses, your calculator could do 7.34 times 10, then raise all of that to the negative 7th. So in your calculator, be careful and use parentheses. If I'm unsure if I need parentheses, I'll go ahead and put them in just to be safe. So from this practice problem, get really comfortable with the meter to nanometer conversion. Also get really comfortable taking a frequency to get a wavelength, taking an energy to get a frequency. So here we use energy to get a frequency, then we use that frequency to get the wavelength. I want to point out this combined form of the equation. Here we are connecting energy, Planck's constant, the speed of light, and wavelength. We could also use the equations separately like we did here, or we could just use this combined equation. Let me show you how this one works out. So energy equals Planck's constant times the frequency. Speed of light, we know, is equal to frequency times the wavelength. Let's try to connect this frequency term to this frequency term so we can show how we get this combined form of the equation. Again, you could use these individually or combined. It's up to your preference. Let's solve for frequency in the second equation, so that is C over lambda. Now let's plug in this into the energy equation. This is energy times Planck's constant. We just solve for frequency to be equal to the speed of light over lambda. So energy is equal to Planck's constant times the speed of light over lambda. That's the same thing as using these equations individually. So it's up to you. If you need lambda and you have energy, you could use this one or vice versa. If you need frequency though, you'll need to use one of these individual equations. 7.2 in the main slide deck is another good practice problem related to this topic. Let's do one more practice problem together because I want to show you how we incorporate that work in there. So using the equation we saw earlier, but we have not used yet. So we saw this one. I told you to do an example with this. So let's see how we can use this equation to solve for kinetic energy, potentially frequency or work. So here we have the work function, that's that capital W, it's in units of joules. Calculate the minimum frequency, so nu, of light required to release electrons from metal. An added detail you would be provided with is at this point, we're going to use a kinetic energy of 0. So you'd be given information like that in order to use the equation we just saw. Then calculate the kinetic energy of the ejected electron if light of frequency of 1.00 times 10 to the 15th per second is used for irradiating the metal. This irradiating the metal just means we have metal. If we're irradiating it, we are shining radiation at it or hitting it with radiation. That is causing those electrons to be emitted from the metal. So that's irradiating the metal, exposing the metal to radiation. Here the radiation has this given frequency. And this is what cesium metal looks like in an ampule. So it's kind of a pretty material, pretty solid. We're going to need that equation we looked at. Then again, you'd be provided with this sort of information. The minimum frequency of light to dislodge an electron is the point where the kinetic energy of the ejected electron is equal to 0. You would not be expected to assume this. Again, you'd be given this sort of information to solve a problem like this. Then, knowing both the work function and the frequency of light, we can solve for the kinetic energy of the ejected electron. So that equation we looked at and we're going to practice with, we can rearrange it to solve for kinetic energy. Again, here we're going to assume kinetic energy is equal to 0. So 0 equals Planck's constant times the frequency minus the work or work function. So the work function here, then plus W to the other side. The work function is equal to Planck's constant times the frequency. So W equals Planck's constant times the frequency. W, the work function, is equal to 3.42 times 10 to the negative 19th joules. I'm going to draw this decimal point a little bit lower, 3.12 times 10 to the 19th, negative 19th joules. Rearranging this to solve for frequency, we need to divide by Planck's constant. So Planck's constant, about 6.63 times 10 to the negative 34 joule seconds. Looking at the units here, joules and joules will cancel out. Then we're just left with 1 over second, which is what we expect for a frequency value. Oops, this should be 3.42. It's shown right there, 3.42. So let me erase this and put in 3.42 times 10 to the negative 19th divided by Planck's constant, 6.63 times 10 to the negative 34. Being really careful about parentheses again, we get a frequency value equal to 5.16 times 10 to the 14th hertz, or the same thing as 1 over seconds. So for A, we needed to set the kinetic energy equal to 0, then rearrange for this equation to solve for frequency. That's the work function divided by Planck's constant. We get this value, importantly, in the correct units of 1 over seconds, which we know is the same thing as 1 hertz. Here's the spelling of hertz, by the way, H-E-R-T-Z, so 1 hertz. Let's try B now. So we have Planck's constant. We were given a frequency to use, and then we're still using that same work function. So this frequency now, 1.00 times 10 to the 15th per second, still the same work function. Then we'll use Planck's constant again. So Planck's constant, our frequency given in part B, then minus the work function provided for us. So just focusing on how the units work out, we're going to see a joule times second for Planck's constant. For a frequency, that's a hertz or a 1 over second. Here, seconds and seconds cancels out. That's just joules minus a value that's in units of joules. So when we're subtracting or adding, those units need to be consistent, and they are here. In the end, we'll get 3.21 times 10 to the 19th joules. So again, that was using this equation and this equation when kinetic energy equaled to 0. So we just practiced using these equations here on slide 19. So you should feel comfortable using these equations given a work function, kinetic energy, Planck's constant, you should know or write on your note card, and a frequency value. Then we can rearrange this as well, solve for kinetic energy, etc. So these equations here are also in chapter 7, and we just practiced using them. So here is where we practice using different versions of this equation. This one we could use when kinetic energy was equal to 0. One recommendation I have for you is to list all the important equations we've gone through so far in chapter 7. Note the meaning of each variable, the expected units of each variable. One specific one to keep in mind is that energy needs to be in joules. It can be in kilojoules, but it can't be in joules per mole, for example. If it's on a per mole basis, we needed to divide by Avogadro's number. So again, expected unit of energy, just joules, not joules per mole. Then some key unit conversions, like we dealt with megahertz. So being clear about what is a hertz, how we go from mega to just hertz, then nanometers to meters, and different important unit conversions like these. So this is a recommendation I have for you. Next, I'm going to go into some animations. I'm including these because they're super cool and for potential interest in them. If we didn't go into certain details that the animation mentions in the lecture, then if we didn't go through something in depth in the lecture recording, then you don't need to worry about it. I just wanted to add these because I think they're cool. So as always, let me know if you have any questions. I'll talk to you next time for more on chapter 7. I'm also including here some animations that are copyrighted and they are provided by the publisher.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
One of the observations confounding atomic scientists in the early 20th century was that an electrically excited element emits light that has a spectrum consisting of discrete lines rather than a continuum of wavelengths. For this to happen, the energy of the element's atoms must be able to change by discrete amounts. Let's see how spectral lines in the visible region of the electromagnetic spectrum arise for the simplest atom, hydrogen. In this thin vertical tube, hydrogen gas has been excited by an electric current. The molecules split into separate H atoms, which absorb electrical energy and then emit light. The spectroscope separates this light into individual wavelengths, which appear as lines in the spectrum. Look through the eyepiece to see the 4 major lines in the visible spectrum of atomic hydrogen. Now we'll explore how they arise. This small bright sphere represents the ground state hydrogen atom. In this most stable state, the atom is in the n=1 energy level, and its single electron occupies the 1s orbital. When the atom is excited, and depending on the amount of energy it absorbs, the electron can occupy one of several higher energy orbitals, such as the 2s orbital, the 2p, the 3s, the 3p, the 3d, and so forth. For example, here, a ground state H atom in the gas discharge tube absorbs enough electrical energy for the 1s electron to occupy the 2p orbital. And then, before it emits that energy as light, it absorbs even more energy, and the electron occupies the 4s orbital. Whenever the excited H atom drops to the n=2 level, it emits a photon with one of 4 specific wavelengths in the visible range. To see how the 4 spectral lines appear, we'll look at some of the possible transitions from higher energy s orbitals, whose boundaries are indicated by the dashed circles, to the 2p orbital in the center. Many other transitions can occur as well. Now, as the film strip unfolds, watch these photons emerge. The lowest energy transition is from the 3s to the n=2 level, and the emission is a photon of red light, which has the longest wavelength. More energy is emitted with the transition from the 4s to the 2p, and it appears as a photon of green light. A still higher energy transition occurs from the 5s to the 2p, and the emission is a photon of blue light. And the highest energy transition occurs from the 6s to the 2p, which appears as a photon of violet light, whose wavelength is the shortest. Lines in other regions of the hydrogen spectrum arise when the excited atom undergoes transitions to other final energy levels. Thus, the ultraviolet lines arise from transitions to the n=1 level, and infrared lines from transitions to the n=3 level. Only an atom whose energy is quantized, that is, exists in certain discrete amounts, can give rise to spectral lines.